the talks, and it will be posted on our website. So it's a great pleasure to have Serge Reynaud with us today. So Serge Reynaud is a director of research at CNRS in France, and since last year he's in emeritus. So he began his scientific career quite some time ago, in 1977, by studying resonant interaction between atoms and photons with Claude Quintalucci, which was a recipient of Nobel Prize in 1997. And so he extended the dressed state approach to include the coupling of atom to vacuum fluctuation. And then he was involved in the first study of radiative force producing cold atoms. Then he studied quantum fluctuation of light, so in the context of quantum optics, and consider the application to very high sensitivity optical measurement using, for example, squeeze states, control of quantum noise. This led him to work on projects of gravitational wave detection and fundamental physics in space, which require extreme attention of the effect of quantum fluctuation. At the mesoscopic scale, quantum fluctuation show up as a Casimir and Casimir polar forces, and actually Casimir is the topic of the talk today. And this measurement, lead to some tests of the quantum field theory, and Serge has developed a lot of theoretical methods to take into account the condition of real experiment, which are quite complicated and sophisticated. I think he will say a few words about that today. And he also studied many applications of this effect. So, during his career, Serge has published more than 200 papers in international peer-reviewed journal, and he has 100 invited contribution in books and conference proceedings. Also, Serge Reynaud has, during his career, has taken many scientific responsibilities, and I don't want to give you all the list now, but just to point out two of these scientific responsibilities. So he represents France at the steering committee of the Casimir network of the European Science Foundation from 2010 to 2014, and is a member since its creation in 2013 of the Science Working Group to supervise the scientific exploration of the space mission microscope. That's what we are talking just now. Where they want to test the equivalent principle, and then they find, so that the preliminary result of this mission find that this equivalent principle is true at the precision on 10 to the minus 15. So with further ado, please, Serge, we are happy to hear what you have to say about the Casimir forces.
Okay, thanks for the introduction and for the invitation. Of course, I am very happy to be with you online and to explain and to give an overview of what has been done in our group on Casimir forces. So, as you already said, I have worked essentially all my scientific life on the effects of quantum fluctuations, which we know quite well in atomic physics. They are responsible for spontaneous emission, for radiative corrections, but they are also the source for big problems in fundamental physics because their energy, the energy of vacuum fluctuations, rises a big problem at the interface with gravitation. So I will begin the talk by introducing Casimir force and this problem of vacuum energy, and discuss a bit relation with gravitation, but very rapidly, and then I will also give you a very short glimpse on experimental tests of this Casimir force and reasons why we have spent so much time on working on this comparison of experiments with theory, because there are still some problems which are not solved. And in the end, I will give you also a short view on recent extensions of the work on Casimir effect to the case of interfaces between physics and biology, where surprisingly, there is an effect of Casimir forces, which was not expected by previous works. So I begin now. I want to say that this work has been done over a large number of years with many people. I want to, of course, quote the name of Astrid Lambrecht, who has been a very important contributor in our group. And also, I want to stress there are many people in many different laboratories in different countries with whom we have worked. You will see some of their contributions during the talk. And of course, I can answer. You can ask questions when you want, and I can answer questions on the topics I will explain, and other ones if you have more questions on this effect. So first thing I want to say is to remind the formula, the Casimir formula, which represents an ideal situation. So the main specificity of this formula is that it is a universal effect associated with confinement of vacuum energy, which depends essentially on nothing, meaning it depends on the fundamental constant of quantum physics and relativity, and also on geometry. So it's formula given by Casimir a long time ago was calculated for perfectly reflecting mirrors, perfectly plane parallel mirrors, zero temperature, also, of course, perfect surfaces. And it has this, this expression. I assume you see the mouse. Yes. So the Casimir energy is, of course, proportional to the area of the plates. It is also proportional to h bar because it is proportional to the energy of vacuum. So there is one h bar, and c because in fact it is not the energy but the linear momentum of vacuum fluctuations, which is important because vacuum fluctuations are exerting radiation pressure on the mirrors. So once you know that these factors here are present in the numerator, you know from dimensional analysis that the energy is varying as the inverse of the cube of the distance between the two plates. And you have only to calculate the numbers here. And I will give you a very rough idea of how we calculate it later. Of course, so this is an energy of vacuum in the presence of the two plates, and the force is the derivative of this energy when you change the distance between the two plates. The result in the end is an attractive force, meaning a negative pressure. And the order of magnitude is given here. So it is a small force. The reason is just that you have a force of microscopic origin that you look at not so small distances. 1 micron scale is large compared to the atomic scales. And this is why the force is small. If you go to atomic distances here, you get a force which is a large force comparable to cohesion forces coming from quantum theory. So this is a small effect, but not so small, and it is now easily seen. I will show you experiments where the effect is seen, and seeing the effect is now easy. Measuring it with good accuracy is not so easy, but seeing the effect is now easy. Okay, I have a problem with the screen, which is blocked. I don't know if this happens for you.
We are still on the same slide, huh?
Yes, this is a problem. It is no longer moving.
Okay.
Maybe I stop the sharing and redo it, and it will work.
Okay, Serge, no problem.
No, it's blocked. I hope it will work again.
Okay. You give me your slides on my.
Yes. So now it's back. Maybe I stop full screen, which might be the source of the problem. It happens.
Okay.
Yes, it works now. So I will go on this way.
Okay.
So here is just a very, very short description of how we calculate Casimir effect, which is an effect of radiation pressure of quantum fluctuations. Quantum fluctuations are not only vacuum fluctuations, but also thermal fluctuations. They are pervading empty space, and depending on the mode, they are reflected or transmitted through the mirrors. And this makes a difference between the energy inside the cavity and outside the cavity. And the force is the difference of radiation pressures on the inner and outer sides. The radiation pressure, if you calculate it, is infinite on both sides, but the difference, the force, the difference of pressures is finite. And this is one very nice advantage of what we call scattering theory, where the effect is determined by scattering amplitudes of mirrors. And the fact that physical mirrors are transparent at high frequencies solves the high frequency problem, which is otherwise very complicated to solve in the general quantum field theory studies. So this is a very nice property of what we call scattering theory, but the main property, of course, is that with this approach, you can calculate the Casimir effect for real mirrors, not only for ideal situations. And you have to take into account the fact that most accurate experiments are performed with gold-covered plates. And of course, the effect is no longer universal because you have to describe the non-universal properties of reflection by a gold plate. Experiments are performed at room temperature, so you have thermal fluctuations besides vacuum fluctuations. All experiments with some accuracy are done in plane sphere geometry, and the calculation, easy calculations, are in plane geometry. So you have to deal with this problem. I will have a slide on this, and I also say, but will not come back on this, that we are now able to calculate plane sphere geometry with accuracy in essentially any situation. But this was a lot of work. And finally, you will see that non-ideality of surfaces, such as surface roughness or patches, are also a problem, and the problem is to be tackled before you can compare experiment and theory. 0-point fluctuations have a long story. They have been introduced by Planck long ago, and for reasons which are now no longer considered as good reasons. But first correct demonstration is old also, and surprisingly, the first correct demonstration is to look at the classical limit of the quantum theory of black body radiation and look for correct classical limit. And this gives you the 1/2 energy of a photon, which is the correct answer that we know now from quantum theory. Now, vacuum fluctuations are just a consequence of Heisenberg relations. There is no mystery, but all these discussions here were before the advent of full quantum theory, and very soon there were predictions of effects which are now routinely observed, and which are direct confirmations of the existence of these fluctuations. Something which is also very old is discovery by Nernst of the puzzle of vacuum energy. So the fact that these fluctuations, which were first discussed for matter, also exist for electromagnetic fields. But now there is a big problem. There is a large number of modes in electromagnetic fields. And when you add up this term per mode on all modes, you give a huge vacuum energy, which is infinite if you have no cutoff, which is finite when you have cutoff, but still much too large to make a correct connection with gravitation. And here are just a few numbers from a conservative estimation. So this is something which was done just in the beginning. You can put bound on mean vacuum energy by gravitational observations in the solar system. You can say that your theory is valid up to some energy. So nowadays we have to take, say, the energy in accelerators, then you have a huge discrepancy between what is bounded by observations, by gravitational observation, and what is calculated by theory. And some people are very proud to have here the largest ever discrepancy between theory and experiment. If you take here the now measured cosmic vacuum energy, so what people in cosmology call dark energy, and a cutoff at Planck energy, which is today the natural cutoff in theory. And here we have this huge discrepancy. This is a problem which is known essentially, which has been known for 100 years, which is still not fixed. And this has given rise to many different ideas. For example, you can use this here and say that you should have a cutoff, which is not this one, but another one, describing the interface of vacuum and gravitation. And this means that this cutoff, which gives you a wavelength of this order, could be a limit where gravity might be affected. So this is an old idea, and now this idea is discarded by what we call short-range gravity test, meaning that you do experiments on all possible situations you can have to test if the gravity force is what you expect in microscopic domain. So here in red, so this is a plot which is always presented by people working on this domain. Here is distance, and here is the ratio of what you look at to the gravity force. So this means that here you are around 1. So this means that you know that gravity is correct here. And if you can see the numbers on the scale, you see that this is 56 micrometers, and we had 85 on the previous one. So the idea is that there is some dark energy length scale around 80 micrometers is now discarded by experiments in Washington, the Earth-Wash group. When you go down to smaller distances, you arrive at tests which are performed by comparing the Casimir force, comparing the theory and the experiments for the Casimir test. And you see that you are eliminating violations, but now at a level much larger than the size of gravity. What you are doing, in fact, is eliminating new hypothetical forces, which could be 10 to the plus 15 larger than gravitational force at these distances. So you see that, and then you have tests done with microscopic particles, neutrons, atoms, and here the numbers are even larger. So what we see here is that the Casimir measurement of Casimir force is one way of accessing this problem of this big conflict between quantum theory and gravitation by doing force measurements at the essentially micron scale. So this is one reason why it is. This is one of the reasons why we entered the domain in the beginning, and of course there are other reasons which will become apparent in the following. The problem is interesting in itself, of course. Okay, so one more. So this slide has too many information, but you can just keep in mind the ideas that you need to describe the scattering of electromagnetic fields by gold cover plates. So you use essentially the Fresnel laws for the mirrors. So these are expressions of the Fresnel laws. They are here just to tell you that everything is fixed. There is nothing unknown here. And this is a big formula of the Casimir pressure, calculated as I explained very shortly before. This is the result of the sum over all modes of radiation pressure of vacuum and thermal fluctuations. So this is a huge formula, but again, everything is fixed in this formula. So you have just to calculate and you get some result. To describe the dielectric function of metal, you have to use a model. So this model is very common. You have a contribution of bound electrons. In fact, it will not raise any problems in the following. You have to use what you know from tabulated optical data here, and you do that and it works. Problem comes from conduction electron. So if you want, a problem comes from the fact that metals have a finite conductivity. So you have to use this formula, and you know a good model for conductivity, which is the Drude model, with two parameters. One is the plasma frequency, which depends on the density of electrons, their charge, their effective mass. So again, this is well known, and this can be measured by measuring reflection on gold. And so this formula, which is important, which is the relation between static conductivity, plasma frequency, and the relaxation parameter of electrons in metal. And of course, as you have a finite conductivity, this means that you have a finite relaxation rate for electrons in metals. Of course, this is basic solid state physics. But there is a big problem, and this problem was somewhat unexpected, that the very small relaxation, so very small means you take the numbers for gold, and gamma is a very small proportion of the plasma frequency, meaning that gold is a very good reflector, as you know. So this extremely small number makes a large effect on the calculation of the Casimir force. Here we plot the ratio of the full pressure calculated by the expression of the previous slide, and here the ideal Casimir formula, much simpler. So this is just to cancel the very fast dependence here of this factor. This is why we make this division. So Casimir formula would be 1 at all distances. And here you see that we are smaller than 1. This means that these are small distances, and this corresponds in the radiation pressure formula to large frequencies. And of course, you know that gold is not no longer a good conductor at large frequencies. So this is the effect here. And there is no problem. This effect is seen very well. But here, there is another problem, and this is the effect of thermal fluctuations. The ideal Casimir formula is calculated at 0 temperature, and here you have the effect of thermal fluctuations, which of course is larger than vacuum fluctuations when the temperature is high enough, or equivalently when the length is higher than the thermal wavelength typical for the problem. So here all calculations are for ambient temperature, and here you have the formula with no losses and the formula with the losses known to be those for gold. And you see that you have a large difference between the two curves, which is well understood, even if there are hundreds of papers debating about what is happening there. And the reason is that we don't see the proper experimental result here, as I will now explain. We see the wrong one. So a very short description of Casimir experiments. I focused on most accurate experiment, which is done in Purdue in the group of Ricardo Deca. This is a microtorsion oscillator. This is a plate with these dimensions. So this is kind of micro electromechanical system, but one which has been designed for accurate measurements. It is obeying a torsion equation, and it has a free oscillation frequency. This experiment is very accurate because it is looking at frequencies. It is measuring frequencies, not directly forces. So you have your plate here, the same one, but the artist view is different here, and not at all at scales. The previous one was roughly at scale. So you have your oscillator, your torsion oscillator here. You measure its frequency when this sphere is very far. You get the natural frequency of your oscillator, and then you approach this sphere. So there is a Casimir force here, and this induces a shift of the oscillation of this system, which is very easy to calculate. It is in fact proportional to the gradient of the Casimir force, and two numbers which are calibrated directly or by other experiments. So in the end, you have this, you are looking at this frequency shift, and this gives you the gradient of the force between the two systems. So there are other details I am skipping, but you can ask questions on them. And then finally, I need something more, which is the description of the force between a plane and a sphere in the situation where the radius is much larger than the distance, which is the case in the experiments. And here we use proximity force approximation, which gives a good result. As I told you, we now have the exact results in this situation, and they are very close to what is given by proximity force approximation. So in this case, we calculate the force as the integral over the distribution of local distances here of the pressure calculated between two plates. So this gives you an expression for the force. And when you look at the gradient of this force, there is a big simplification because the gradient of the plane sphere force is proportional to the pressure between two planes. So you have a way to compare theory and experiment, which is very direct. And this is the way the experiment was performed by the group of Deca. And the result is a kind of problem because experiments do not fully agree with theory. So here you see the plot on the same paper of comparisons at various distances. At short distances here, it works well. And then at larger distances, you see a problem. And the problem is that the error bars here correspond to experimental results. And below, there is a full line corresponding to the model without losses. And the correct theory, with which is taking into account the losses, is here, and it is neatly different from experiment. So you have a rough confirmation at a level of around 5%, which is not so bad. You have a rough confirmation of theory of Casimir effect, but with a big problem, which is still not mastered. So there has been a large number of things which has been studied, a lot of them by our group, but other people have done also important work in this domain. A lot of suspects have been considered. It could be new forces. Of course, it would be just extremely exciting, but most people do not think it is due to such an effect. It is more probably related to something which is still not well done in the experiment or in the theory. And here are a list of things which have been investigated very deeply. I will give you one in the next slide, just to give you an example. I could have done this for any of these problems, but I focus on this one, contribution of electrostatic patches, because it is, again, a problem interesting in itself, on which much progress has been done thanks to the discrepancy in Casimir experiments. So the patch effect is due to the fact that surfaces of metallic plates are not equipotentials, because real surfaces are made of crystallites, which have different orientations and then different work functions. For ultra clean surfaces, which is a case studied by people in solid state physics, you see that topography, as seen by atomic force microscopy, patches, as seen by Kelvin probe force microscopy, which are seeing directly the potential at the surface, and electron backscattering are directly related. You see, you understand what is the origin of the problem, and the origin of the problem is the crystallites. You see quite well here. When you are working in situations which are not ultra vacuum, ultra low temperature, which is the case for Casimir experiments done at ambient temperature in good vacuum but not ultra vacuum, you have to imagine you have contamination over these surfaces, and of course this affects the patches. And this effect has been known for decades to be a limitation for many precision measurements. And I think we were among the first to do quantitative work on this patch effect, just to try to solve our Casimir problem. First thing we did was to model the patches, give a correct result of a correct description of patches, and looking at the possibilities that patches are explaining the difference. So on this plot here, as a function of distance, you have the difference between theory and experiment, which is the black curve. And so you see that there is a difference which is extremely well defined, since here you have uncertainty represented by the dispersion of points on the black line. So there is an effect. This was a description of patch effect in the papers, original papers. It was much too small to explain the fact. If we take the same parameters for the patches, but the correct model we designed, you have this curve, which now is too large. So this means that depending on details on the patches which were not known at this time, patches could have been the explanation, and this is the best fit where you change the parameters and you can have a best fit explaining essentially perfectly the black curve. So the difference. But this is a model, this is not a real thing, so we went further and measured the patches, which had essentially never been done at that time. So this is a map of electrostatic potential on gold-covered plates, which are similar to those used by Ricardo Deca in the Casimir experiment. Samples were provided by him, and they were not the samples of the experiment, but the samples with similar properties. And so we did Kelvin probe measurements, and then with these maps we calculated the effect of electrostatic interaction between the patches on the two planes. And here is a final result of this study. And you see again this curve, which is the discrepancy between the experiment and theory, and the curves here, which are the calculation of electrostatic pressure between the two plates when you use parameters you have measured on the plates. And you see that this is 10 times smaller than the difference. So there is a contribution, but it cannot explain the discrepancy. Okay, now I have finished my first part on Casimir measurements between gold-covered plates in vacuum, and I want to spend the last minutes explaining something quite different. So first thing I want to say is that Casimir forces are present at many different places in physics. And here I want to focus on the interface of physics with biology. Of course, we are no longer in vacuum. We are in salted water with many ions, and screening by ions play, of course, a crucial role. So you have to redo the whole analysis, taking into account the fact that you have longitudinal modes corresponding to the motion of ions in the electrolytes. And these longitudinal modes are coupled to the electromagnetic transverse modes. So you have a new kind of modes. They are coupled. And what we did is to generalize the scattering approach to describe this coupling and calculate the force in the end. And in the end, we found a formula which looks like the one which has been written before. We calculate in the presence of, with a large concentration of ions, which is not a decision. This is just what we are interested in, the interface with biology. And in the case of biology, the concentration of ions is so large, then the Debye screening length is of a fraction of nanometer. So any electrostatic force is screened extremely efficiently. So most people, having worked on this problem before, thought that Casimir effect was screened also. And what we have shown is that there is one non-screen contribution of transverse magnetic modes at 0 Matsubara frequency. So this is a new effect in theory. And here is the consequence for the effect of Casimir forces. This blue curve is the calculation by the new theory as a function of distance. And this green curve is what was calculated by previous theory, which is essentially the same thing, minus the new non-screened force. And at small distances, the two curves are in agreement, and most experiments done up to our new theory were done at very short distances, and the two curves agree, so there is no way to distinguish them there. But I will now show you results of an experiment which has been done at large distances, and you see that at large distances, the two curves are neatly different. So this work was first theoretical done between our group and the group of Paulo Maianeto, working in Rio de Janeiro. And here is a presentation of the experiment done there in Rio de Janeiro, in collaboration with many people, because there were many things to be mastered and calculated for getting something useful from these experiments. You imagine that these experiments are extremely difficult because you are now measuring force in water and not in vacuum. So your objects are directly coupled to water, and of course it is a challenge to do this measurement. Idea which was used in the group of Maianeto is to have optical tweezers and to trap a small sphere, in an optical tweezer and look at fluctuations of this sphere, fluctuations of position of this sphere. So this is a histogram of positions as measured over time. This is a curve, not really a curve, where you see position versus time. And here is an interpretation of the result, which is just the relation between probability distribution in this histogram and the potential you have to put in Maxwell-Boltzmann equation to explain the distribution. And here you have just a simple potential, which is the potential well known for the optical tweezer, essentially quadratic variation of the potential, which is trapping the small sphere at the center, at the focus of the beam. Now you approach a larger sphere, which is adhered on your mechanical setup here. You approach it from the small sphere, which is held by the optical tweezer, and there is an attraction, and you can measure it by looking at the modification of the fluctuations of the small sphere. So as I said, we are in ice salt concentration corresponding to the typical case of biological interfaces. Screening length is extremely small, so all electrostatic forces are screened, in particular the double layer force, which is coming from the surfaces of the two spheres, and which you see if you have larger device screening length. The experiment has been done to check, and it works. So when you have good eye screening, you no longer see it. And here is, in the end, the curve with there is no fitting on this curve. This is there is nothing unknown. This is just a direct comparison between theory and experiment. Here you have in black the scattering theory, in blue the experimental points, and in red the curve calculated without the new term. And you see extremely well that there is a confirmation of the theory, and in particular there is confirmation of the new term, which is quite clean. Again, realizing that you are measuring a small force of a small sphere in water. So this is completely different. Of course, the accuracy is not at all the same as in the previous experiment, but of course, situation is completely different. Okay, now I have finished. So I have essentially conclusions on the first part. We have now a test of Casimir force with a global confirmation, but there is still a problem resisting the analysis, and we need new ideas to solve these problems. And the new thing is that Casimir force is present at the interface between physics and biology, and that this new work completely changed the understanding of the effect of device screening on Casimir forces. And I expect that this will have important effects in coming years on this domain. So thanks.
Thank you very much, Serge, for this very, very nice talk, very interesting. So the session is open for questions now. So you can use the chat or you can directly ask your question. So maybe I will start then. I have actually two questions regarding the first part of your talk. The first one is that I was a bit surprised by when you showed hypothetic new forces in terms of Matsubara potential. So you say atomic physics is at the range of 10 to the minus 11 meter. So I was wondering what kind of experiment is it corresponding to? So that's my first question. Yes, here, exactly. So when you say atomic physics, right? So it's a very, very short distance.
These are essentially experiments with atoms, but certainly not the best one you can do today. These are old experiments. So this is always in our plots because, of course, this is part of the knowledge, and but I am sure we can do much better with current technology, of course.
But this is not Casimir-Polder interaction here, right? It's kind of spectroscopic measurement inside the atom itself? Or?
Yes, you are right. You are extremely small distances, and this is more the effects on spectroscopy. Yes, you are right. But it is clear that experiments with neutrons, for example, with air, which are the best here, can be done with atoms probably easily with codes. No, these are not easy experiments, but these are experiments which are certainly possible now with cold atom technology, and which were not years ago.
I see. I have another question. So related to this systematic mismatch between theory and experiment that you discussed in details. So you are presenting some kind of very simple system, experimentally speaking. I mean, it's just a plate and a sphere. I also see some paper where people are using more sophisticated system, you know, with some kind of micro mechanical system where they're going inside. So it's completely different geometry. I mean, maybe it's not as precise, of course, as Descartes experiment, but I mean, is it that this experiment also shows some kind of shift, and is it similar problem?
No, you are right. This is an important question. So, as I told you, there are now a large number of applications of Casimir effect in various configurations, and in particular, configurations which are of interest for micro electromechanical systems or atomic physics close to surfaces. So there are many proposals. There are some experiments. These experiments are not as precise as the Descartes experiment, but they are bringing interesting information. But essentially, they are not solving the problem. For example, if you have atoms, essentially you don't see the conduction electrons in the metal, and you don't have this critical problem of large factor 2 due to dissipation. So these experiments are extremely interesting. They will certainly be more and more frequent because we now have technologies allowing for these experiments, and they are in the large domain of new quantum technologies. So I am sure there will be new things. I am not sure they will solve the problem of interaction between the conduction electrons.
Yeah, okay, I see, of course. Okay, so other questions? Berger?
Hi Serge, this is Berger Englert. I very much enjoyed your talk. So I haven't been aware of all these developments. I'm very impressed. I want to ask you something about something that was not mentioned in your talk, but was for a short time, some 30 years ago, a hot topic. You remember the work by Scharnhorst and Barton, who predicted that light propagating between the two Casimir plates is a little bit faster than Einstein allows, right?
Yes, of course.
It's what I remember. It is a very tiny effect, like 1 part in 10 to the 30 or maybe 10 to the 36, something like this. So it didn't look like anything that can be measurable by existing technology and in those days or even today.
Yes.
But in your community of Casimir physicists, what do you make of these papers? I mean, is the effect even correct? And are there circumstances where one could see such a thing? I mean,
yes. Again, this is very good question. There was a lot of activity around these questions years ago, but this activity has declined because most important work has been done theoretically, and there is no way to test the effect experimentally. Another domain which has been extremely active and less active now is the domain of dynamical Casimir effect. So
that would have been my second question.
Okay, I let you ask your question.
No. I mean, you already started talking about it. I mean, this idea that if the mirrors are accelerated, then you get photon pair emission, right?
Yes. So when your mirror is moving you have only one mirror, and you see it, you make it move in vacuum, and you expect to see effects which are very important because they reveal that vacuum is not empty. you are moving in vacuum. If it was classical vacuum, nothing would happen, and it is
has to be
vacuum.
Accelerated motion, right?
Yes, as soon as you have accelerated motions, there are things happening, and this has been a huge topic of theoretical interest during a lot of years. And the experiments have not been done with real mirrors, because the effect is too small with real mirrors, because real mirrors cannot move at large velocities. And of course, you need to approach velocity of light to see something measurable. So the experiments have been done on analog systems, first in the group of Per Delsing in Göteborg. And the idea is you take squid-like systems, and you make a motion of an apparent surface by field modulation. And this experiment has been able to prove that the Casimir dynamical Casimir effect was indeed existing roughly as predicted. So this is interesting, but this is not the original idea of motion in vacuum. This is different idea, which is mimicking motion by squid-like effect. But of course, this is very interesting, because this is proving that essentially it works as predicted by theory.
Okay, thank you.
Okay, so thank you, Berge. So we have also now Bing Sui.
Yeah, so hi, I'm Bing from NTU. So thanks very much for your very interesting and insightful talk, especially your mention about the existence of this unscreened zero Matsubara frequency TM mode. So I have a question pertaining to the second part of your talk, which pertains to electrolytes. Yeah, so I'm curious about what sort of salts did you investigate? So you mentioned salt solutions. So there are different kinds of salts.
Yes, this is the experiment is essentially with ordinary salt, but of course it can be done with very different solutions. Essentially, what we have does not depend on the solution. It is fixed by the fact that screening is very efficient. So you need many ions. The details are not so important. But of course, you are right. For example, for applications to real biology, you would have to take a lot of extra details into account, of course.
Yes, so because even in theoretical modeling, there are different physical consequences depending on the kind of salt. For example, there's monovalent salts and also polyvalent salts. So for theoretical modeling of monovalent salts, usually people can neglect the ion-ion correlations. And then yeah, because I saw that this is Debye screening length. And then in polyvalent salt solutions, yeah, there are additional effects arising from the stronger correlations between ions. For example, there could be deviations from the Debye screening law. Yeah, so because this was not really discussed in your talk, but probably I should look at your papers. Yeah, so for
no, but you are certainly right. There are many things beyond what we have done. What we have done was just first study of Casimir forces in electrolytes, and we have seen something which is big difference with previous knowledge. But you are absolutely right. We have now to work on details, in particular correlations between ions. This is for sure. We are just beginning to do this kind of studies.
Thank you.
Yeah, thank you, Bing. There is a question in the chat, so from Thomas Zanon. Maybe I will read the question. So, is dynamical Casimir effect is somehow related to the Hurun effect with accelerated detector near a black hole? So that's a bit.
Yes. This is part of this big domain of dynamical Casimir effect, which was studied a lot for years, and so there are still people trying to make experiments in this domain, which is not easy at all. And again, I guess that there will be new observations, maybe again with cold atom technologies, which allow new things to be done. So I have heard of many proposals, but I have not heard recent results on this. But I am sure that they will come probably soon.
Okay, thank you, Serge. So there is another question in the chat box. So I will read the question for you. So, can experiment on the dynamical Casimir effect demonstrate properties of dark energy?
Yes, this is another big domain of the interaction, of the connection, potential connection between Casimir effect and cosmology. And here there are not hundreds of papers, but thousands of papers and many different ideas. I don't think that the problem is solved now, but there are probably people having different ideas and probably new ideas to come, because dark energy is there for sure. This is an observation which is completely clear now, and there is no explanation. So idea that it could be related in some sense to vacuum fluctuations is completely natural. There are thousands of papers on this idea. So there are many possibilities. Probably none of them has convinced community up to now, but this will probably change.
Okay, thank you, Serge. So any other questions? You can ask directly or type in the chat box. Okay, so since I have another question actually. I mean, when you do the theory of the patch, I was expecting like somehow this electrostatic effect will be more important, or will give more important contribution if you are close at shorter distances. Whereas at shorter distances, we see that there is no problem at all. So I mean, and here when you show your result, you show it at long distance. No, it's not at long distances actually. It's rather no, it's at long distances. Sorry. So I mean, what's happening for your model at short distances?
So here you see essentially a power law in log-log plot. So when you are going to smaller distances, you have larger and larger effect of patches. And on these topics, there has been measurements by people working on cold atoms trapped on small surfaces. And I think that we are globally in agreement with what they did measure. And the effect can, of course, become large when you are at smaller distances. And this is a problem for the small traps in particular the networks of small traps which are built for quantum information purpose. So this is a very important problem for people working cold atoms, and there have been a few experiments, and we essentially agree with their results in different regimes. Of course, we are at larger distances, and we see a mean effect of all the patches. They can be sensitive to the details of what is happening on a given surface. We are just considering a statistical average of all the pages. So this is somewhat different, but there is a good agreement between our works.
Okay, so I think if there is no other questions, so thank you very much, Serge, for this very nice talk. Have a nice day, and
okay.
then hope to see you soon, maybe in Singapore.
Thank you again for invitation and nice opportunity to discuss.
Salut, Serge.
And,
thank you.
And hope we will see in person sometime from now.
Yes, hopefully, yes, hopefully.
Thank you and bye-bye.
Bye.
Ok,
bon, ben merci.
Merci beaucoup, Serge. C'était très bien, très intéressant. Je pense qu'il y a eu quand même quelques questions, donc c'était bien. Ok, écoute, on se tient au courant.
Ok,
puis,
sûr.
Voilà, si je passe à Paris, écoute, je viendrai te saluer.
D'accord.
Merci beaucoup.
Salut.
Au revoir.
À bientôt. Au revoir.